I'm very excited for today. Today, we're going to talk about something that is near and dear to me, which is building an open system, and especially for quantum technology, and an ecosystem. So today we have Misty, and I'm going to go through that. So if you're watching this on YouTube or anywhere else, I'm the host, Taposh Roy. I am uh, director at Kaiser Permanente, and my focus of my work is digital twins, machine learning, and long-term. I was the head of products in a prior startup, and I worked as a consultant as well. I'm the author of the book Medical Image Processing with Deep Learning, and I'm currently writing a book on intelligent governance for both quantum and the classical ecosystem. Um, I have a volunteer. She's been worked with me for quite some time now, almost 6 months, and she's a student and middle school and helping me with getting things organized. So thank you for that, Divya. Today's agenda. So today we'll have Misty from Unitary Fund. She's going to talk to us how Unitary Fund is building an open quantum ecosystem. Then we'll have some fireside chat, few questions here and there, and then we'll open it up for the audience for questions, and we'll take it from there. So an overview of the session. So this is going to introduce us to Unitary Fund, which is a not-for-profit organization, and it's helping to create a quantum technology open source ecosystem that benefits the people. Unitary Fund, if you go to their site, you'll see also provides microgrants for explorers in open quantum technology, leads open source software and research projects. They have a community forum. They use Discord for that. So do try to sign up for that if you're interested. What will the attendees learn today? And this is something I'm thankful to Misty for putting this together. You're going to learn about Unitary Fund definitely, right? And then you're going to learn about two major softwares. One is Mitiq, which is a Python toolkit for quantum error mitigation, and Mitiq, a web platform for community-driven quantum benchmarks. I'm very interested in Mitiq, and I know Misty is a developer there. So there is a lot of potential in Mitiq that I see. And I was telling me Misty that we should compare it with some uh, maybe professional software as well. About Misty, Misty is a member of the technical staff at Unitary Fund. She's a developer, as I said, for the software package Mitiq. She's a researcher in quantum error mitigation. She is expanding the Mitiq suite of error mitigation techniques, and also how it's been used across with different software packages, be it IBM Qiskit or Cirq. She also does host some talks as well. So she has a video series, if I'm not mistaken. So definitely Google her, you'll be able to find more details, or I have a LinkedIn from her, and then we'll definitely hear from her and she'll provide us all the details as well. With that, I'll pass it on to Misty and we'll take it from there.
Thank
Misty,
you very much for the introduction, and thanks everyone for joining. All right, so yes, as Taposh already mentioned, this is about building the open quantum technology ecosystem and what we at Unitary Fund are doing to help with that. So we do that in a number of different ways. We are, like Taposh said, we're a nonprofit organization helping create a technology ecosystem that benefits the most people. And so we do that by providing microgrants, which I'll talk a little bit more about later in the talk, but they're $4,000 for rapid projects in quantum technology, so 3 to 6 months in duration. And then we also have our in-house but fully open source projects, Mitiq, which is Python toolkit for quantum error mitigation, and Metric, which is a web platform for quantum computing benchmarks that anyone in the community can submit to. And then finally, we host a lot of community building events, which I will also talk a bit more about in future slides. This is the Unitary Fund team. So we are leaders in the quantum open source space. So our president, Will, was formerly at Rigetti. He launched the first quantum cloud services platform there. Our CTO, Nathan, is lead developer on Qtip, and that's one of the most influential packages in quantum information, and many other experts here too. So we're really happy to share our expertise with the community and help it grow. We also have am I muted?
Sorry, I was trying to mute myself and I muted you. I'm sorry for that.
Oh, no worries. Okay. So yeah, as I was saying, we have a thriving volunteer community, and we really, really appreciate and recognize our volunteers. And so we have ambassadors, the ambassadors to be announced in 2022, Alberto Maldonado Romo, Amir Ibrahimi, Nick Gardner, and Rahul Mistry. And they are PhD students or software developers in the quantum space, but most of them were new to quantum computing when they first came and started working with Unitary Fund, just as contributors to the Mitiq package, or I think Alberto was actually a Microgrant winner at one point. But we also have a thriving community of our Microgrant awardees, and we also have an advisory board of volunteer experts across the industry, academia, and government labs. And they're experts in quantum systems and software. So they help review applications for microgrants, but they also serve as mentors to our micrograntees and to pretty much anyone in our community who pops up on the Discord, pops into a community call, which I'll explain in just a bit what those are, just to give an overview. So microgrants, these are $4,000 for small projects and quantum technology. You don't really have to have any specific credentials to be able to win a microgrant. We fund all kinds of explorers. It's just that it has to be a project in open quantum technology. It has to be something around on the order of 3 to 6 months, and in duration, and something that we think will benefit the community. And of course, you do need to know how to execute the project, and we have advisors to help. But we do, want our grantees to be well equipped to do what they've set out to do. But you don't have to have a specific degree. In fact, we encourage people from other backgrounds to get involved in this way if they have an idea and if they have the skills to execute it. And certainly other skills we can help with and we can help advise. So it's not like you have to have everything. It's just kind of a pretty well thought out project plan. And we've gotten amazing results from this program. We have 72 microgrants, 23 countries. So pretty much any country can apply to this. Anyone from any country can apply to this. Of course, we have to comply with certain guidelines, but yeah, we welcome applications from all over the world. We have over 17 our microgrant winners have over 17 publications as a result of their projects. That's not to say that these are all that research focused, they're research related, but it's more of an outgrowth of the libraries, over 30 libraries, and other tools that they've developed as part of this program. And also, while we do not fund startups in this way, there have been a couple of startups that have spun out of microgrant projects. So as long as the grant winner keeps their project, like what they actually were funded to do, open source, they are welcome to build on top of that, you know, as they wish. So we just want to see that the tool that we helped you develop stays open source. And also one nonprofit, which is QWorld, came out of this too. So QWorld is a really great quantum education platform. And I think they're also global. So it's in virtual. It's really amazing to see what they've been able to do since their grant. Yeah, so no strings attached. We don't ask for equity or anything like that. You know, it's for explorers. Yeah, these are mostly open source software projects. I think we're exploring one open hardware project, but we also like to see community building projects. We like to see educational initiatives. All that we ask is now we have a lot of projects out there. So take a look at what we have. You can go to unitary.fund/grants and take a look at past projects and see, like, you know, if if your idea has already been executed before, if there's some way that maybe you could build on what's already out there. So that's one thing that we're kind of looking for now, is kind of synergies between previous projects. So just keep that in mind. But if you have an idea, please go ahead and apply at unitary.fund/grants. And we try to keep the application process as lightweight as possible. So it's just a few minutes application, 2-minute video. Tell us why you're excited about it, why we should be excited about it. And we'd love to hear from you. Right. Sorry, the animations are a little bit off here, but I just wanted to feature a few of our microgrant projects, because sometimes it's a little bit difficult for people who are not familiar to understand. But we had a software package called QRAND for quantum random number generation. PK, people interested in quantum universal education. So that is providing free educational materials online, and also organizing virtual events for anyone who wants to learn quantum computing. Toucan was a little bit more of a research-oriented project, but it also resulted in a software package called Toucan. So that's a quantum circuit compiler for 2 local Hamiltonian simulation problems. And our last one, mirror circuit benchmarks for VQAs, variational quantum algorithms. So this one was actually an idea that a high school student had after he took the qubit by qubit course, which is actually another program that Unitary Fund has supported. And he proposed to develop this benchmarking suite for our in-house open source toolkit, Mitiq. And so he got a grant to do that, to kind of build that out. And he's been really successful with that. And now he's a student at University of Michigan, and he's doing research in quantum computing. And I think he's just finishing up his freshman year. So these kinds of projects can really help get people who are outside of the field, or kind of, you know, adjacent to the field, just getting in like much further into quantum computing. And I just wanted to mention, you can find out more about these featured projects, and I'm sure there'll be upcoming episodes soon on our Unitary Fund YouTube channel. And you can see like what our grant winners have, what they did and what they learned from it, and what they're up to now. So some other exciting things that are going on in the Unitary Fund community. So we host a number of open source projects on our Discord. We have community calls for them weekly, and we have channels, forums to discuss questions, issues, ideas for new functionality, and just get people excited about open source, quantum open source software. And so one of those is Q-tip, and that has over 1 million downloads. So it's been really, really amazing to get connected with Q-tip. And yeah, I think that's a great example of something where we've benefited from having them on our Discord, but also we've been able to give them a platform and a kind of a home for their community, a hub. Another thing that we do is an annual hackathon, and I'll give a little bit more details about that in a few slides, but that has over 30 participating projects, and it's a open source hackathon. So rather than us devising challenges in quantum computing or related topics, we actually go out to our community, we go out to our project maintainers, and we say, what are the things that you would really like someone to solve that you don't have time to solve, or you think would be a really good experience for someone to try and work on? And so we actually give prizes for people to complete those issues. And that's a way that we bring folks into the community. Another thing that we do is the Quantum Open Source Software Survey. That was new last year, and that's to get a snapshot of everyone who uses quantum software technologies. And we got over 1,000 responses on our first try. So definitely a lot of people seem pretty invested in that. And in fact, it gave us a really interesting snapshot of our community. Definitely a lot of researchers and quantum software developers. That's not surprising, but also a good number of students and educators and hobbyists. And so, yeah, we want this to be a really organically growing community, and we want to include as many people as possible. So this has been really helpful to us to see, okay, like there's, places where we can really focus and encourage folks to get involved, contribute. And yeah, I mean, also just kind of where folks go to find out, what more about a particular software package, and where we might be able to also, say, hey, like maybe you should check out this other project that's related. So yeah, we're really excited to have heard from our community, and yeah, I think this will continue to inform the work that we're doing. Now, hopefully this is one of the things that everyone is wondering about. So we have a hackathon coming up, just less than 2 weeks, and we call it Unitary Hack, and it's a completely virtual hackathon. And like I mentioned, it's for open source quantum projects. And so we really want to get people excited about the different open source projects that are out there and contribute to them and start making connections, and connect with maintainers, connect with other hackers, and really get integrated into the community. And we do award cash bounties for closing GitHub issues. So all of these open source projects that are part of Unitary Hack, they have projects up on GitHub, and then they indicate which issues are for the hackathon competition. The first accepted pull request, so the first accepted code submission on an issue will get the cash bounty for closing that issue. And we've had the event twice before, and in 2022, we had over 30 participating projects, 66 bounties, 400 participants, and yeah, over $3,000 in bounties distributed. So it's a really great event. It's super exciting, and there's lots of activity on the Discord and on the project GitHubs. So I really encourage you to check it out and hopefully win a prize. So now I'm going to shift gears a little bit and talk about some of the stuff that we do in-house at Unitary Fund. But when I say in-house, it's still fully open. So we strongly encourage people to check this out, but also to contribute, ask us questions if things are not clear, and let us know, about your experience with these projects and what you would like to see. So it's just, when I say in-house, it's just like the staff are driving the high level direction. We're the ones who are fixing the bugs and adding some of the bigger features, but we really want this to be the community effort. And in fact, Metric is our quantum benchmarking web platform, and you can find it at metric.info, metric with a Q. And we like to say that it's like Papers with Code, but for quantum. So it's a place where people can, if they see a paper on the archive or somewhere else online, they can upload the results from that paper if they're, reported or if they're represented graphically. They can do that and submit it to this platform, and we just have to include the URL, the abstract, the title, like some basic information, and then the results. And this is a way for us, for everyone, to be able to see the state of the art in quantum computing. And in fact, this is the chart for quantum volume. And I think it's kind of a little bit of a old graph. It's still from 2022. So obviously, there's a lot more to be done, and there's probably many data points missing on this graph, but it just gives you a sense, right, of the trend of quantum volume over time. And so I would say, if you notice that something is missing on this graph, a key result, please upload it to Metric and submit it. The submission process is designed to be as simple and as intuitive as possible. We have the YouTube video of how to do it, just to help with the first time submission, but it's pretty straightforward. And you can actually help people get a really clear picture of how quantum technology is progressing in a particular metric, like quantum volume, just at a glance. And now about Mitiq. So this is our other in-house open source project at Unitary Fund. We do a lot of research around error mitigation. So Mitiq is a software package for error mitigation. It's in Python, and it's for applying different error mitigation techniques. It's compatible with many front ends, Cirq, Qiskit, PyQuil, Bracket, PennyLane, OpenChasm, and I'm sure there'll be more. And it's designed to be backend independent. So you could run it on a quantum computer simulator, you could run it on real hardware, and Mitiq will apply the techniques either way. And so we have zero noise extrapolation, which is probably the most well-known and often used error mitigation technique. We also have probabilistic error cancellation, Clifford data regression, which is like a machine learning based technique, digital dynamical decoupling, which I'll get into in a little bit. You may have heard of dynamical decoupling at the pulse level, but this is something a little bit different. And then readout error mitigation, which is our newest technique. Okay. And so the idea here is that error mitigation is like a layer between the user and the back end. So the user generates a quantum program in a front end like Qiskit, and then sends it to Mitiq, and Mitiq will generate quantum programs. They'll generate these intermediate circuits, send them the back end where they're executed, and then it will perform an inference on the noisy results, and then ultimately giving an error mitigated results. So that's where Mitiq kind of sits in the software stack. All right, so just an overview, quick overview of error mitigation techniques. So zero noise extrapolation, the idea here is noise scaling, probabilistic error cancellation, and using quasi-probability representations. So this is for noisy gate level representation, and then canceling the errors through sampling. Learning-based methods like Clifford data regression. We also have a sub-technique for probabilistic error cancellation in Mitiq that is a learning-based technique. So it's actually learning the quasi-probability representations. So somewhat of a similar idea, but these are actually under separate technique headings. Symmetry-based techniques, which we don't have yet in Mitiq, but a student group is actually working on one of these. And then dynamical decoupling and randomized compiling. So for zero noise extrapolation, so the key assumption here is that the noise is Markovian, so the system follows the Markovian master equation, and in the ideal case, the noise scale factor lambda is 0, but on real hardware, lambda is 1, so it's just the noise of the hardware. And the idea with your zero noise extrapolation is to increase the noise beyond the level of the hardware, and then extrapolate back. So we get expectation values at those higher noise levels, and then extrapolate back to the zero noise limit. And that's what should give us close to the ideal value that we want for the calculation. And so, yeah, experimentally, this has been accomplished. The increasing of the noise has been beyond the level of the device has been accomplished by stretching, something called pulse stretching. So stretching the control pulses a bit longer, that increases the effective noise. But there's also a way to do this at the software level, something we called digital ZNE, digital zero noise extrapolation. And that is by inserting additional gates in the circuit in such a way that the gates that we insert compile to identity, but by inserting these extra operations, if they're not compiled out, then they'll actually increase the noise level of the system. And so if we just do that at the gate level, we call that local folding. If we do that at the circuit level, we call that global folding. And so, yeah, so Mitiq does not do pulse stretching. It's not at the pulse level, like it's at the gate level. I just wanted to emphasize that. So it does the gate folding to evaluate the program at higher noise levels. And then once we have these expectation values that have been evaluated at higher noise levels, then we can extrapolate back to the zero noise limit. And Mitiq has a lot of built-in functionality to do that. So can do a polynomial fit, we could do an exponential fit or a polyexponential fit, depending on the shape of the curve that we get with from the noise scaling. And right now, there's still a bit of trial and error in doing this, but we've recently introduced a calibration module, which I don't have a slide on here, but actually helps with selecting the parameters and selecting the extrapolation method. to try and take some of the guesswork out of applying the right parameters and the right technique. And this is just an example of what global folding looks like in Mitiq. So we have a circuit, a very simple circuit, Hadmard, and then a C0. And then if we apply folding, global folding, and we can see that we have the circuit and then the inverse of the circuit and then the circuit again. And so the result in the noiseless case should be identical to the first circuit, but actually the bottom circuit on a noisy hardware or a noisy simulator is going to have a higher noise level because of the extra operations in there than it would on the top. Probabilistic error cancellation, as I mentioned, is another technique that we have in Mitiq. A little bit less common to see, but the idea here is, again, it works on expectation values, estimating expectation values, but the way it does it is a little bit different from CNE. So it's representing ideal gates or an ideal quantum circuit in terms of noisy implementable operations. And these representations are called quasi-probability representations. Quasi because they can have negative values. And those negative values are where we're going to actually get the cancellation. So again, here's our Mitiq workflow. So we have a quantum program of probabilistically, so we generate the circuits and then probabilistically sample them, execute them on the back end as part of that, and then get the measurement results back and do an inference on that, which is, in the case of PUC, is a Monte Carlo average, and we get an error mitigated expectation value from that. And so in Mitiq, this looks like operation representation objects. So we have our quantum circuit, and then we say, I want to represent this gate, and I assume that I have local depolarizing noise. And then I think that the noise level is 0.1. And here's my ideal operation. And then Mitiq will return the line at the bottom where that Hadmard gate is actually represented in terms of, like, I think here it's Hadmard X, Hadmard Y, Z, and so on. And so that's kind of like that's a representation of that ideal gate in terms of the noisy gates. Now, as you can see from these lines of code, you need to know what kind of noise model you have for PUC. You need to know what the noise level is, you know, or at least approximate it to get a good result from PUC. So that does make this technique a bit more expensive to implement, because a lot of times that kind of information comes from tomography. But one way around this is actually to apply some learning routine to at least get a more accurate noise level. It's not necessarily going to tell you what kind of noise you have with the functionality that we currently have in Mitiq, but it can at least tell you what's the best way to represent your gates in terms of the noise level. So now I'll move on to another technique we have in Mitiq, which is digital dynamical decoupling. You may have heard of dynamical decoupling at the pulse level. So inserting additional control pulses to try and keep the qubits from kind of wandering around, rotating around during idle windows in the circuit. This is kind of a similar idea, but it's done at the gate level. And so we have these digital dynamical decoupling sequences of gates. And again, these, if you look, they compile to identity. But by inserting these sequences of gates in the idle windows of the circuit, we can do something similar to what's done with dynamical decoupling at the pulse level. And actually, this technique was mainly developed by one of our community contributors, Aaron Robertson, and he was a 2021 Unitary Fund ambassador. So this is a great way for the community to get involved. I just want to underline that because I know I've been talking a lot about kind of more research-oriented stuff and the software itself, but I just want to mention that this was mainly an initiative of someone who doesn't even work, at Unitary Fund, but just really enjoys working on quantum software and help develop this technique. And here's another one of our techniques that's upcoming, and it's from our ambassador, Purva. So she's a PhD student at Southern Illinois University. So again, another person from the community who stepped in and helped us out with this. And this is kind of like a screenshot from her document that she put together for identity scaling. But the idea is that this is another noise scaling way of scaling the noise for zero noise extrapolation. So we already went over folding. This is inserting identities. So it's actually kind of the opposite idea of digital dynamical decoupling. So now we're inserting idle windows in the circuit, essentially, to increase the noise. But remember that then we can extrapolate those noisy expectation values back to the zero noise limit. And this is a lot of information. So I would say, definitely, if you're curious about Mitiq, if you want to know more about error mitigation, a great place to start is our tutorials on mitiq.readthedocs.io. And we have, I think we're up to 20 examples. They're not all on the slide, but, and they're all different techniques. There are a number of different applications, variational quantum algorithms, benchmarking. We have one where we integrate with Biscuit, which is a compiler. So different hardware backends, different front ends. So I think this really is a great place to start and get a sense of what you can do with Mitiq, which is actually a lot for a quantum software toolkit that came out a few years ago. So. And quantum error mitigation, I mean, it's a useful, it's useful for variational quantum algorithms. It's also useful for benchmarking. And so we've had a number of experiments, both in-house and elsewhere, where Mitiq has been helpful in improving the results of benchmarking experiments. And one of them actually was Emily Huffman. She did quantum simulation of real-time dynamics for strongly coupled lattice gauge theories. And so she was actually able to improve the results by using Mitiq, by using our zero noise extrapolation module. So she was able to get closer to the ideal. So that's a really, I think that's a really powerful example of what Mitiq can do. And it can really push the limit of the results that we're able to get out of our current and near-term hardware. We've also done our own testing of error mitigation on hardware. So we've limited that to zero noise extrapolation, probabilistic error cancellation for the most part, at least in terms of in terms of papers. But I will say I did do a small test of digital dynamical decoupling on IBMQ, and that also looks pretty good. And I have an example up on Read the Docs if you're curious about what that looks like. But in terms of kind of more systematic testing, it's been zero noise extrapolation and probabilistic error cancellation. And we've done that on randomized benchmarking circuits. We've done that on mirror circuits. We've tested it on IBM-Q, Rigetti, and IonQ. And this is just a list of all of the experiments. And so we can see that, when we benchmark Mitiq, we get, a pretty nice improvement factor from ZNE. So the improvement factor is just the ratio of the square root of the mean errors without mitigation over with mitigation. So we can have the comparison there, and that accounts for the fact that we may have additional executions if we're doing error mitigation, like if we're doing sampling or withholding with CNE. So we try and distill that into this improvement factor, and we can get up to 7 times improvement. So that's pretty exciting. And this was on a 3-qubit device. I think this was on IBM-Q. You can also see that with CNE, the expectation value is much more nicely around 1 compared with the raw value as the Clifford depth increases. So as you add more operations into the circuit, it gets noisier and noisier. It's also true for ZNE, but with ZNE, we can extrapolate back. So we can kind of get back to that ideal expectation value of 1. It's kind of the intuition here. And I know I'm running short on time, so I'll just go very quickly and just say this is our newest research with Mitiq. We just put this up on the archive last week, and it's zero noise extrapolation on logical qubits by scaling the error correction code distance. And so this is actually combining quantum error mitigation with quantum error correction. So sometimes people who are not as familiar might actually mix those two, but those are generally thought of as very different schemes and for very different regimes. So with quantum error correction, we're thinking about like fault tolerant quantum computing. We're thinking about large scale devices. And for quantum error mitigation, we're thinking about NISQ. We're thinking about small scale, noisy, intermediate scale, noisy stuff. But this is looking at, okay, as we scale up devices, we continue to do that, not as fast as we like, but we do that. As we get better and better qubits, then what do we do in that in between? And so one way is to actually try and unite those methods. So that's what this is doing. And if you're curious, you can look at the paper. It's up on archive. I have the link there. So, okay. So kind of coming back to open source, right? So we've heard about Metric, we've heard about Mitiq, we've heard about Microgrants, but why is open source even so important? And so I would say that because you can make a difference, because you can help build all of these amazing research tools that are going and educational tools that are going to help us get to the next level when it comes to quantum computing and push the field forward in a way that everyone can use, everyone can access. But it can also advance your career in quantum, in software, and a lot of other things. And I know that for myself because I was actually a contributor to Mitiq from the community, wanted to get into quantum. I took some courses, online courses in quantum, but I really needed that experience. And that's how I did it, was I actually contributed to Mitiq, I got to know the team, and eventually I became technical staff at Unitary Fund. It took a year, but it's something that really is doable if you keep at it. So I just want to really underline that for those who are trying to get in and don't know how to do that. It is possible. It's fun. I think we have an amazing community. You can really connect with people and you can solve interesting problems. So what can you contribute? Well, code, right? It's open source software. So this is a great way to develop coding skills and show off your coding skills. But you can also contribute infrastructure like GitHub Actions. You can contribute documentation like the examples list that you saw. There's actually a lot of explanations in those examples of why do we choose the options we do? How does this function work? Where can you find out more information? UX design, we have a UX designer who also became a designer through her volunteer work at Unitary Fund, and now she's doing that full time for her career. Data, so submit your data to Mitiq. If you find a paper online that you really like, you can also just upload that. Mitiq will, will properly credit everyone, credit the authors, but it'll help the community to have that information in the database in a way that's easily viewable. User feedback, also one that sometimes doesn't get enough attention, but is very helpful. So if you find a bug in Mitiq or on the Mitiq platform, or with any other project, open a GitHub issue, ask your question on Discord. And I know that our maintainers would be happy to hear from you. So how to get started? Well, you can find a project on GitHub. You can join a community on Discord. There are many forums. We have many events and community calls, the weekly community calls, in fact. And conveniently, a hackathon is coming up starting on May 26th. So that's also a really great way to get involved. So it's, there's lots of other people who are asking questions and kind of lower that barrier to like, oh, I don't know what to ask or whether I should ask. Those events can be a great way to just jump in and get started. So in conclusion, open source communities continue to add value to the quantum tech ecosystem, and your contributions can help them grow. Wherever you may be in your quantum journey, your contributions do count. Thank you.
Misty, really thank you for this awesome talk. I know if it was not open source, we wouldn't have had Python today. We wouldn't have had Linux today. So I think that's a huge call out to you and the Unitary Fund team for doing this. And I know there are a lot of people who are aspiring to get into quantum computing. And I think this is one of the best ways to do that. And hackathon is always the best way because you would basically partner with someone and you will learn along with them. So definitely do check out Unitary Fund. I have a few questions for you, Misty. So first question that I have for you is, I know Unitary Funds does microgrants, but who's funding Unitary Fund?
So good question. So we have a combination of corporate sponsors, individual donors, and government grants. So the government grants are for our in-house research, like some of the things you saw with like benchmarking Mitiq, or even like kind of the core lead developers of Mitiq. But yeah, the microgrants come from corporate sponsors and individual donors.
Got it. So if I know there are quite a few participants here, and then there are participants who watch it on the video as well on YouTube. If they are interested in sponsoring Unitary Fund, what's the best way and whom to reach out to?
Yeah, that would be great. I would say email info@unitary.fund, and that goes right to our chief of staff,
Okay.
and he can walk you through the process.
Okay. And so you said about the hackathon coming in a couple of weeks, right?
Yes.
And for hackathons, I'd like to ask you, how does one sign up? I mean, is there maybe there is a link we can put it here, or you have it here in your talk? You can put it there. Yeah.
Let's do that. So it's unitaryhack.dev. And let me find the chat. There it is.
Yeah.
So that's the link.
Yeah.
Sign up there.
Perfect. And can somebody sponsor a hackathon, or can somebody sponsor software for that? How, if somebody's interested here, how would they do that? Same thing?
Yeah, it would be the same thing. Yeah, we would love that.
Okay. Okay, now I'm going to ask a little maybe technical question. So zero noise extrapolation, ZNE techniques,
Mhm.
right? I know you talked about the global folding as well, and the pulse folding part of it briefly, right? Are there comparisons? Which is there one better than others? What's your take? And I know you had a paper that combines everything, but just a
Yeah.
high level idea. Yeah.
So for zero noise extrapolation, I mean, the sometimes it's better to have hardware control, but realistically, if you're on the IBM Q experience, like you're not going to be able to access the low level hardware. So it's much more convenient for the user to be able to do this at the gate level. And as we saw, like it's pretty powerful. I mean, we can get up to 7 times improvement
Yeah.
factor just by doing folding in ZNE.
Okay. Thank you. Thank you for that. I'm gonna now open up for the questions from our guests who are participating. So let me see if anybody wants to raise their question, or I can start reading from from the comments out here. I'm gonna give you everybody a second to see if anybody has a question they want to ask right away. Okay, Ron has a Ron, do you want to ask a question, or do you want to? It's a statement. So
I did have a question about the global folding. Do you just assume that the error at the end of global folding is equally distributed across the timeline, or do you apply some sort of coherence degradation algorithm to it?
Um, I mean, as it is now, we just assume that it's the same. We have introduced some circuit layer folding functionality very recently, but even then, it's pretty basic.
Okay. Yeah, and my comment was, it's my understanding, at least from listening to Qiskit people, that there is a layer at which you can control the laser pulses on the IBM hardware, and I forget the name of it. But I've seen a couple of
Oh,
talks where they
open
talk about
pulse,
doing
I think.
open
Yeah.
pulse, yeah, something like that. So that's pretty close. So
Yeah, I haven't used it myself. And I suppose it is possible to apply implement some sort of ZNE with it. We haven't tried that. We've kept it, at the gate level also because you can convert much more easily between different front ends and use different back ends without kind of worrying about translating pulses.
yeah, okay, great. So one last question from me, and then I'll let someone else go. On the Unitary Fund grants page, it looks like there's a number of predefined topics, and so my question is, can you submit any topic, or is it
You
more
can
likely
submit
that?
any topic. Yeah.
Excellent. All right, thank you.
hey, so I think one of the questions that is there from FY, you want to ask your question, or you want me to read it? Okay, I'm gonna read it since, okay, so the question is, how much knowledge for quantum computing theory do I need to have to participate in these projects? And I think you answered it in some way already.
Well, so it depends on depends on the project. So I would say like for metric, you don't really need to know too much. I mean, all you need to, I guess you do need to know enough to be able to understand like what is being, the result that's being achieved and like what is the task. But I think like those kinds of things, they don't require a lot of mathematical background. It's just kind of more understanding the terminology that's used and kind of recognizing the patterns of, okay, like that's how people describe experiments in the literature and results in the literature. For Mitiq, also not too much. We have some issues on our GitHub that are software only, and we deliberately do that also for Unitary Hack. We mark some like non-quantum is what we call it. But then if you want to do a microgrant project, then you will need to have background in whatever it is that pertains to your project, but not necessarily. I mean, no one can know the whole field of quantum computing. So it's more like that specific area that you would need to know.
Yeah, I think that's an important point. I think if you're trying to learn everything, that's not going to happen.
Yeah.
Even I think some of the leaders have actually mentioned, right, that it's very hard to understand quantum totally. I think Friedman himself said that back in the day. Another question, I think this is from Jai Kumar. Jai Kumar, do you want me to read it? Okay, I think I'll read it then. So I think his question is on funding educational programs and activities. Is that possible through Mitiq? As I'm assuming it's a microgrant now. Yeah.
Through the micro. We have in the past. We generally don't fund one-time events. So we want something that's going to have some permanence in the community, and that's open to everyone. And so generally not focused on a specific region or institution or things like that. But yes, we do fund educational projects.
Yeah. So I mean, you might have said this, do you fund projects which are purely not just research, but strategy as well?
We would definitely do that. Yeah.
Okay. Any other question from anyone? This is the time, last 3 minutes. You can unmute yourself and go ahead, ask Misty. Okay. Think people have all their questions answered.
All right.
Okay, so thank you, Misty, for your time, and thank you for explaining us more details about Unitary Fund. I'll love to connect with you later on for some of the projects I'm working on. So definitely looking forward to working with you in the future. Thank you, everyone. Thanks.
Thank you for having me. Thanks for listening, everyone. Okay.
Thank you.
Bye-bye.
Bye.